I'm going to begin the lecture today by backing up just a little bit from where we were last time to fix the problem that we're working on, and it is to understand how a pressure difference across a membrane induces a concentration gradient and then flow of a liquid through the membrane. And so the situation we're looking at is one where we have a membrane that's shown here, and it has a liquid on either side of it, water in the case of desalination, and we impose a high pressure on one side called PF, and we'll typically refer to that as the feed side of the membrane, while the back side of the membrane is maintained at a lower pressure, P sub P, which is often called the permeate pressure. And in many cases, such as desalination, and in the experimental data we'll look at, this permeate pressure is just ambient pressure. In the case where there might be salt in the water, and the membrane permeates water but not salt, the concentration of water in the feed is actually a little bit lower than it is in the permeate. The permeate would be almost pure water, while the feed would have some salt in it, so the concentration of water would be lower here. Osmosis would normally want to drive water from the high concentration side to the low concentration side, but by applying a high pressure to the feed side, we can actually drive water from the low water concentration side to the high water concentration side. And we do this by setting up a concentration gradient in the membrane that I'll explain in a little more detail. And then the transport just occurs by Fickian diffusion. Now, in the what we'll be talking about today, we're only going to consider the case where both the feed and the permeate have pure liquid solvent, so pure water or a pure organic solvent in the case of some of the experimental data we'll look at. And so the only term that will matter in this performance equation is this first one involving the delta P across the membrane. The delta pi term, which would relate to the presence of solutes such as salt in the water on either side of the membrane, will be zero. And what we're trying to do is reconcile the transport of a liquid through the membrane according to Fick's law and the performance equation that's typically used to describe, for example, water transport through desalination membranes, where the water flux is found to be linearly proportional to the pressure difference across the membrane, and this constant of proportionality A is often reported in the literature as the membrane permeability or membrane permeance. So that sets the problem that we're looking at. A key thing that to note that we're not going to discuss in detail here is a result from mechanics, and that is that if you have a dense or non-porous polymer membrane and you apply a high pressure to one side of it, and the back side of it is supported in some way such that the membrane simply can't move as a result of the pressure difference, then that pressure is actually transmitted entirely through the membrane to the back face of the membrane. So the penetrant that is dissolved in the polymer at this back face is experiencing the hydrostatic pressure on the feed side. Now that's a result from mechanics, and we won't go into depth of that, but it is in fact true. And so there is a pressure gradient or pressure discontinuity at the back face of this membrane, and any penetrant that is sitting in the polymer right at the back face is experiencing the feed pressure, and penetrant that is in the water or solvent phase just next to the membrane is obviously at the lower permeate pressure. Turns out this pressure discontinuity is incredibly important in setting up this concentration gradient, and therefore the Fickian driven transport of solvent through the membrane. And I showed you these experimental data because they're counterintuitive, and this is a situation where Rosenbaum and Cotton were studying the water transport through cellulose acetate, which was a first generation reverse osmosis membrane, and they measured the concentration gradient across a membrane under two different conditions. One where the feed pressure was about 68 atmospheres, one where the feed pressure was about double that, 136 atmospheres. In all cases, the permeate pressure, the downstream pressure, was 1 atmosphere. And what they observed is that as a function of pressure, the concentration of water on the feed side, that is the high pressure side of the membrane, didn't change much, and it wasn't very different from just the water uptake in cellulose acetate. If you had a membrane of cellulose acetate and just soaked it in a bowl of water at ambient pressure, and so pressure had almost no impact on the concentration of water on the feed side of this membrane. However, as the feed pressure increased, it actually reduced the concentration of water on the permeate side of the membrane, and this is what establishes the concentration gradient in water that then drives the flow of water from feed to permeate as a result of Fick's law. And so we started last time talking about how we thermodynamically analyze this situation to understand this apparently counterintuitive result. That is, as you raise the pressure on the feed side of the membrane, the concentration of water on the permeate side drops. We see that this is not restricted to cellulose acetate and water. These are results from Don Paul in the early 70s. And here they're also measuring the concentration gradient of now an organic penetrant across cyclohexanone across a cross-linked rubber membrane, and they're finding exactly the same result. That is, as they apply a high pressure to the upstream side of the membrane, the concentration of solvent in the membrane is very close to the value it would have if you just took that rubber and swelled it in cyclohexanone at ambient pressure. So pressure is having virtually no effect on the solvent volume fraction at the upstream side of the membrane or high pressure side of the membrane, but it is decreasing the solvent concentration in the membrane at the downstream side. So this is a general phenomena related to liquid transport through solvent swollen membranes. And we started the analysis of trying to reconcile the application of Fick's law for transport of water or solvent through the membrane with the performance equation that we find, for example, in reverse osmosis, where the water flux, in the absence of any salt in the water, that is where this delta pi term is 0, the water flux is just linearly proportional to the delta P across the membrane. Typically the permeate pressure is often ambient, and so this delta P changes because we're raising or lowering the feed pressure. And as we raise the feed pressure, we have faster or more flux of water across the membrane. And so that's the situation that we're trying to describe. And we note the pressure profile across the membrane, what must be the concentration profile to drive transport by Fickian diffusion, and also now introduce the concept that at the solution polymer interface, both on the feed side and the permeate side, we have to have continuity in chemical potential, and this will be the key to the analysis, the thermodynamic part of the analysis at least, is this continuity or equality of chemical potential of penetrant in the water next to the membrane and penetrant dissolved in the polymer at that water membrane interface or solvent membrane interface in the case of the organic liquids. We noted that the effect of pressure on swelling of polymers is often weak. That is the effect of swelling by liquid penetrants. And we turn to the work of Ham, who measured the swollen polymer volume at a pressure P relative to its volume at atmospheric pressure, and they applied really enormously high pressures, going up to 30,000 psi in this case, and noted that in the case of rubber swollen with chlorobenzene, as the pressure went up, the volume of the sample decreased, but it decreased only slightly. Here at 25,000 psi, the volume of the polymer sample is still 96% of its volume at ambient pressure. And we'll focus on these equilibrated lines that are labeled S here. They also noted, or we can take this back to the applications in water by replotting Ham's data as shown here, and noting that for desalination the region of interest would never be greater than about 100 bar or so, and so one would expect, based on the data we just saw, that there'd be incredibly little change in the volume of penetrant uptake by the polymer over this very narrow pressure range. Ham also noted that in the case of a different rubber, neoprene, that was swollen with chlorobenzene, that the swollen polymer volume could actually increase a little bit with pressure. So in some cases, the swollen volume will go down with pressure slightly. In some cases, it goes up slightly. So this is the experimental data. Or in the case of Paul and Ebrelima's work and the work by Rosenbaum and Cotton, the swollen polymer volume, or the amount of solvent uptake or water uptake, really didn't change at all with pressure. And so we have three different cases. One is the sample can uptake somewhat more penetrant as pressure increases. Another case is there can be essentially no change in penetrant uptake with pressure. And the third case is there can be a slight reduction in penetrant concentration with pressure. And so the model that we're going to use must reconcile all three of these experimental observations if it is in fact a general model. And we start by working on the feed side of the membrane. We're going to equate the chemical potential of solvent or water in the feed with that in the membrane right at this interface. Now when we finish this, we'll come back and work on the low pressure or permeate side of the membrane. Then we'll combine those results and be able to essentially predict the experimental results I've just shown you. Just as a reminder of how chemical potential is affected by pressure, the derivative of chemical potential for a pure component with respect to pressure is just the molar volume of that component. That's, the molecular weight, I guess, divided by the density. In a mixture, for example, with a penetrant dissolved in a polymer, the change in the chemical potential of the penetrant with respect to pressure is the partial molar volume. And so this is going to be a key for us. Molar volume is the pressure dependence of chemical potential in a pure substance. Partial molar volume is the pressure dependence of chemical potential in a mixture such as a penetrant dissolved in a polymer. Differences between these two are what actually drive the difference in swelling behavior with pressure. And so we start by considering a case where we have a membrane exposed to a uniform pressure of a pure solvent like water, for example, and we can write an expression for the chemical potential of the water with pressure. And as we increase the pressure in the water, its chemical potential just increases according to the definition of chemical potential, where VW is the molar volume of the water. We can also write an expression for the effective pressure on chemical potential of water dissolved in the membrane, and it looks very similar, except the molar volume is replaced by the partial molar volume. The reference pressure can be any value you want. We're going to set it to the permeate pressure, or what would typically be ambient pressure in our calculations for convenience. And so we write an expression, and I must apologize for the change in nomenclature here. That is inadvertent on my part. We write an expression for the chemical potential of water at the feed side of the membrane, and we write it as the reference chemical potential, which we take to be the chemical potential of water at the permeate pressure, which will typically be ambient, plus the molar volume of water. I'm sorry, I've called that VW here. The molar volume of water times the pressure difference. Now, in reaching this expression, we've started from this one, and we've assumed that the molar volume is independent of pressure, so it comes outside the integration, and you get directly to this expression. Now, for the case of the water or penetrant that's dissolved in the polymer at this feed interface, the first and third terms in the chemical potential look exactly the same, except now the molar volume is replaced by the partial molar volume of the solvent in the polymer. We must also recognize that for a penetrant dissolved in a polymer, that the chemical potential of that penetrant inside the polymer can also change depending on what the concentration of penetrant is in the polymer, and so we include that through inclusion of an activity term, and this activity is then linked back to the concentration of solvent in the polymer through an appropriate thermodynamic model. And so for a polymer solvent system, this might be the Flory-Huggins, or for a cross-linked polymer network, it might be the Flory-Rayner model. So we'll need a thermodynamic model to ultimately relate the thermodynamic activity back to the actual experimentally measurable or determinable concentration in the membrane. And so we recognize that there must be a quality of chemical potential at this feed interface, so we equate the chemical potentials at the in the pure solvent and in the membrane. The expressions from the previous page are brought forward here, and we combine them. The reference chemical potential drops out, and after a bit of algebra you get the expression that's at the bottom of this page. And we'll look at that in a little more detail here. This is about where we stopped last time, and equating the chemical potential of solvent in the upstream or the high pressure face of the membrane equal to that of the solvent just dissolved in the upstream face of the membrane leads to this expression. And it says that the RT times the logarithm of the thermodynamic activity of solvent in the membrane right at this high pressure interface is equal to the difference between the molar volume and partial molar volume of solvent, or in this case water, times the pressure difference across the membrane. Now, if the molar volume of water and the partial molar volume of water dissolved in the polymer are exactly equal to one another, then what it says is that the activity of water in the membrane right at this feed interface is independent of feed pressure. So you can raise the feed pressure as high as you want, lower the permeate pressure all the way to vacuum, and there's absolutely no change in the thermodynamic activity of water in the feed side if the molar volume and partial molar volume of the water are equal to one another. Now, remember that using something like the Flory-Huggins model, as the thermodynamic activity of water or solvent in a polymer increases, the concentration of the solvent or water will increase. Not necessarily linearly, but there is a general trend that as activity goes up, then the concentration of penetrant dissolved in the polymer will increase. And so if the molar volume and partial molar volume of water are equal to one another, what it says is the activity of water at this feed interface is independent of pressure, and therefore the concentration of water dissolved in the membrane will never change no matter how high the pressure goes. On the other hand, if the molar volume of water is a little bit larger than the partial molar volume, then if we increase this feed pressure, the water activity in the polymer has to increase, and that means the concentration of water or solvent in the polymer has to increase. We saw an example of this in some of the work by hand. On the other hand, if the partial molar volume is a little bit less than if the molar volume is a little bit less than the partial molar volume, then as you raise the feed pressure, drives the activity of water at this interface down, drives the concentration of water in the polymer down. And the way this would show up in Ham's experiments is as the concentration of the water went down, the swelling of that water of the solvent swollen sample would decrease. So this qualitatively explains the three cases that are outlined here and that we saw in the experimental data. This is a case from Rosenbaum and Cotton when the water molar volume and partial molar volume in the polymer are about equal to one another. Then as you increase the pressure, on the feed side of the membrane, there's virtually no change in the concentration of water because there's no change in the concentration of there's no change in the thermodynamic activity of water at this feed interface. Similarly, in the work by Paul and Ebrelima, the molar volume of cyclohexanone was about equal to its partial molar volume in the cross-linked rubber they're using, and so the amount of cyclohexanone dissolved in this polymer at 400 pounds was about equal to that would be dissolved in the polymer if you just had the sample soaking in cyclohexanone at ambient pressure. In the case of Ham et al., in the chlorobenzene in heavier rubber, there was a slight decrease in the volume and therefore the amount of solvent in the sample as pressure increased, and that indicates that the molar volume of chlorobenzene is a little greater than the partial molar volume. And Ham et al. Looked at a very wide pressure range. If they had been down in the 100 atmospheres or so that Rosenbaum and Cotton were studying, or the few hundred psi that Paul et al. Studied, they would have seen essentially no impact of pressure on the concentration of chlorobenzene dissolved in this polymer. In the case of neoprene, the chlorobenzene molar volume is a little less than the partial molar volume, and so over a very wide pressure range you see a slight increase in the amount of chlorobenzene sorbent in the polymer. Again, note that go to 30,000 psi and the volume of the sample only increases by 3%, so these are tiny effects really, and at the pressure ranges we're normally interested in, there'd be essentially no effect of pressure on the concentration of penetrant in the feed or high pressure side of the membranes we're interested in. And so again, I've just summarized that key result here because we're going to need it in a moment. I'd like to just take a moment to contrast this with the case of gas solubility in polymers. So we've talked a good bit about that earlier in the semester, and I've shown you data like this in a number of different formats where as we always plot the concentration of gas dissolved in the polymer as a function of pressure, or for non-ideal gases like the butane here, particularly at low temperature, we use fugacity, which is just pressure times activity, thermodynamic activity coefficient of the gas. And what we find invariably is that as pressure increases, the concentration of penetrant dissolved in the polymer increases. For reference, about 50 cc's of gas at STP per cc of polymer is about 10 weight%. But we just routinely see in the cases of gases dissolving in polymers, as we increase the pressure, we increase the concentration. So why the difference? What difference does it make if there's a gas dissolving in a polymer and a liquid dissolving in a polymer? Once the penetrant is dissolved in the polymer, it cannot possibly know that it came from a gas or a liquid, and therefore can't know whether it should go into or out of the polymer based on the phase of the substance. And so how do we reconcile this with the observation that if we had liquid butane sorbing into this polymer as a function of pressure, we should expect to see essentially no change in the concentration of butane dissolved in the polymer as a function of pressure. We come back to exactly the same analysis, and we start at the same point, that is equating the chemical potential of butane, pure butane gas, at a pressure, I'll call it P sub F, or fugacity in the case of a non-ideal gas, equating the chemical potential of the pure butane just next to the membrane with the chemical potential of butane dissolved in the polymer at that same pressure. And a thermodynamic analysis would lead us to exactly the same equation as we got for the case of water or solvent uptake from liquids into polymers. Now we will compare the molar volume of butane with the partial molar volume, and this is going to turn out to be the key difference. The partial molar volume of butane in silicone rubber has been measured. It's reported in this article, and it's on the order of 115 or 120 cc's per mole. That's the partial molar volume of butane in PDMS. Measure that through swelling experiments. Basically expose the polymer to butane at a given pressure and measure how much the volume of the polymer penetrant sample has increased. And you'll remember that partial molar volume is defined as the change in the volume as a result of change in the number of moles of, in this case, butane in the polymer. So we can measure partial molar volume directly. Now, remember that number, 115, 120 cc's per mole. Partial molar volume of butane in PDMS. What is the molar volume of butane in the gas phase? Now, at 35 degrees C, butane is, over this narrow pressure range, behaves more or less ideally. And so I just use the ideal gas law to calculate the molar volume of butane in the gas phase. Look at these numbers. At 1.2 atmospheres, near the upper end of the pressure range I showed you on the sorption data a moment ago, the molar volume is about 21,000 cc's per mole, and at the lower, towards the lower range, it's on the order of 51,000 cc's per mole. Partial molar volume on the order of 120 cc's per mole. So unlike the liquid case, where the molar volume of the liquids was about equal to the partial molar volume, in this case the molar volume of the gas is enormously larger, orders of magnitude larger than the partial molar volume of the gas dissolved in the polymer. And so now if we come back to this expression, the log of the activity of butane in the polymer is depends on the difference between the molar volume and partial molar volume of butane in the polymer. And if the partial molar volume of butane is essentially negligible, then it means that any time the pressure is increased above the reference pressure, the activity of butane will increase. And so as the activity increases, so goes the concentration in the sample. And so this this result is, I'm showing you really a shortcut version of this. It assumes that that the molar volume and partial molar volumes are independent of pressure, and while that is approximately true to a very good approximation for the partial molar volume, it obviously can't be true for the molar volume. And just as a hint, a good homework problem is to go back through the derivation of this expression and modify it to take account for the molar volume being a function of pressure, for example, through the ideal gas law. And so the reason we see gas sorption increase with increasing pressure, while liquid solubility is essentially independent of pressure in polymers, is due to this difference between molar volume in the gas phase and the molar volume of a penetrant in the liquid phase. Now let's go back to the liquid transport problem. We've answered the question. One half of this problem is, why does the concentration of water or solvent dissolved in a polymer not change with pressure at the feed side? The other half of it is, why does the concentration of water or solvent decrease with pressure on the permeate side? And so we'll attack that problem in exactly the same way that we attack the feed side version of this problem. That is, we will equate the chemical potential of the solvent or water inside the membrane at the downstream or low pressure side of the membrane equal to that of the water that's in the that's in contact with it. And again, remember that this pressure profile for the solution diffusion model is that the feed pressure is transmitted through to the backside of the membrane, and there's a discontinuity in pressure at the permeate membrane interface, and the penetrant molecules that are dissolved in the polymer are exposed to the feed pressure, while those that are in the contiguous liquid phase are exposed to the much lower permeate pressure. And we'll look at another set of really old data. This is data from Gaiman, where they put a a rubber sample in a porous metal sample holder and surrounded that by liquid by a solvent at ambient pressure, and because this sample holder was porous, the liquid could transmit across the sample holder and dissolve in the polymer. And as that happened, then the polymer is constrained here. It's trying to absorb this solvent, which it likes very much, as we'll see in a moment. And at the same time, its volume is constrained. And so what happens is, as the polymer sample absorbs solvent, then the pressure inside the pressure, hydrostatic pressure, builds up inside the polymer, and this can be detected with an instron. An instron's a device, has a force measurement device that can be used to sense the force exerted per unit area by this sample. And so what Gaiman was doing was allowing the solvent to imbibe into the polymer as it wanted, and then measuring how much pressure that induced with this instron. And then he would move the instron piston a little bit, and that would reduce the pressure that the membrane was experiencing, and it reduced pressure. That would mean that the chemical potential of the penetrant inside the polymer was lowered, and the sample could then absorb more penetrant. And he reported these results in the following way. The volume fraction of rubber as a function of the swelling pressure that he measured with his instron. And I've converted the volume fraction of rubber into the volume fraction of the solvent, in this case toluene. You can see that these volume fractions, from 55 to 75%, the sample has more toluene in it than it does rubber. But what it shows is that as the pressure inside the swelling pressure exerted by the membrane, as that is higher, the amount of solvent that the polymer can take up from this reservoir that's next to it at ambient pressure goes down. And just as a bit of foreshadowing, the Flory-Huggins model is used to make a prediction of this swelling pressure. So again, it's we can use thermodynamics to analyze these data, and it's a cross-linked rubber, and so he's using actually using the Flory-Rayner model, which accounts for cross-linking. This is the molecular weight between cross-linking. What he calls mu is what we have been calling, what most of the world would call, the Flory-Huggins chi parameter. Now let's come back to our analysis of the chemical potential of solvent or water right at this downstream interface, and we'll proceed exactly as we did before. We'll write the chemical potential of water in the permeate side of the membrane in the pure water case as the reference chemical potential plus the molar volume of water. And if we take our reference pressure equal to the permeate pressure, this second term goes away, and so what it says is the chemical potential of water at the permeate face of this membrane is just equal to the reference chemical potential. For the chemical potential of water that's dissolved in the membrane right at the permeate side, that chemical potential expression looks exactly like it did when we did the analysis at the upstream side. And so we combine these two results and do the algebra, and the final result is shown here. And now we see the key result that tells us why increasing the feed pressure lowers the concentration of penetrant at the permeate side of the membrane. The result here says that if we raise the feed pressure, this negative sign on this exponential means that the activity of solvent or water in the membrane at the downstream face of the membrane decreases. Raise the feed pressure, note the negative sign here, raise the feed pressure, lower the thermodynamic activity of water in the membrane. And as the activity of water in the membrane goes down, As feed pressure goes up, the concentration of water in the membrane has to go down. And this has been described in the literature as you raise the feed pressure, you're squeezing the water out of the downstream side of the membrane. And so what's happening here is as the feed pressure raises, the pressure experienced by water that's dissolved in the membrane at this permeate interface, as the feed pressure goes up, the pressure experienced by that water goes up, its chemical potential goes up. The chemical potential of water in the contiguous phase to the sample does not change as the permeate pressure changes. And so if you've raised the chemical potential of water inside the membrane by raising the feed pressure, and it's trying to equilibrate with water at a lower pressure, the only way it can do that is by adjusting the concentration of water, lowering the concentration of water in the membrane to reduce the thermodynamic activity, to reduce the chemical potential of water in the membrane until we get back to equality of chemical potential. So as the feed pressure goes up, essentially as the feed pressure goes up, the thermodynamic activity goes down in order to keep the chemical potential of water in the membrane just equal to that in the permeate phase. Now, how important or how big is this effect? If we look at the case of Rosenbaum and Cotton, the partial molar volume of water is roughly equal to the molar volume of water, and that would be about 18 cc's per mole at ambient conditions. And so you can use this expression to predict how the thermodynamic activity of water will change as the feed pressure increases. And by the time we get to around a feed pressure of 100, which would be about the top pressure you would see in desalination, the activity of water at the permeate side is dropped from 1, since it's being equilibrated with pure water on the permeate side, is dropped from 1 to about 0.93. So is this a big deal? Well, this is a prediction by the Flory-Huggins model of the volume fraction of penetrant dissolved in a polymer as a function of activity for various values of the chi parameter. Now, for chi parameters that are less than a half, they would predict that if you put a polymer in contact with a liquid, with a solvent at unit activity, the polymer would just dissolve in the solvent. And so that's why these volume fractions start at 1. Now, in a practical situation, the ones that we've been looking at in these strongly swelling cases, like the rubbers being exposed to organic liquids, those materials were all cross-linked, and so it would be more appropriate to use something like the Flory-Rayner model. I'm just doing this to show the effect of pressure on volume fraction for several different chi values, and so the effect, the amount of penetrant dissolved in the polymer is shown as a function of activity, and I've converted that for the case of water to what the feed pressure would correspond to, holding permeate pressure always at 1 atmosphere. And so what this says is that there could be significant changes in the volume fraction of water even as the activity changes from 1 to 0.95 or 0.93. So those small changes in activity towards the high end of the activity scale give rise to significant changes in concentration of penetrant dissolved in the polymer. Now, this is a summary of how pressure difference across the membrane causes a concentration difference, that the high feed pressure of liquid does little to change the concentration of penetrant on the high pressure or upstream side of the membrane, and if the feed is pure penetrant like pure water, then the activity up here is always 1 by definition, and as the feed pressure increases, the concentration of penetrant on the permeate side of the membrane goes down according to the expression that's shown here. A minor point is whether or not this concentration profile would be linear, and to answer that intellectual question, we turn again to the work of Paul and Ebrelima who, in addition to analyzing the thermodynamics of this situation, also developed a transport model to describe the transport of pure liquid penetrant through a solvent swollen membrane. And this model starts with a basic application of Fick's law to a system that has a solvent being imbibed by a polymer. The nomenclature used by Paul is somewhat different from what we've used. I'm showing the correspondence here for the flux. He writes mass flux, whereas we've been writing volumetric flux. They're connected just by the molar volume of the solvent, as shown here. The mass flux of solvent is equal to the weight fraction of solvent times the solvent plus polymer, or solvent plus rubber in his case, flux. This is a standard convection correction to Fickian diffusion. You'll find this equation, for example, in binary transport out of classic textbooks like Bird, Stewart, and Lightfoot. And the second term in this equation is just the concentration-driven Fickian diffusion term. Now, at steady state, when the membrane is operating, the flux of polymer, or the flux of rubber in sub r, will be equal to 0. And so in the next slide, that assumption has been made, and the flux expression has been rearranged to account for the fact that the polymer sample is stationary, so it has no flux. Paul also shows that this expression can be written in terms of volume fraction, as shown here, and he then goes on under the limiting circumstance where the diffusion coefficient of the penetrant through the polymer is taken to be a constant. This expression can then be integrated to calculate the volume fraction profile through the membrane, and ultimately the weight fraction and concentration profile through the membrane. And it turns out that it's not strictly linear, but in fact, when if the volume fraction of the penetrant that is absorbed by the polymer is small, then you can expand this term in a Taylor series, and it turns out that the concentration profile is in fact linear when the when the amount of penetrant uptake is small. Now, for Paul is writing everything in terms of volume fraction, and we've been talking in terms of in terms of concentrations based upon, for example, grams of penetrant absorbed per unit volume of polymer. And those two are connected by the partial specific volume of the penetrant. We talked earlier in terms of chemical potential. We were talking about the pressure dependence of chemical potential being written in terms of the partial molar volume, and the partial specific volume is just the partial molar volume connected by the molecular weight. So these two terms, one is a mass-based and one is molar-based, but they're essentially proportional to one another, and you can use them interchangeably with the appropriate factor of the molecular weight. And so in a material that is highly swollen, like the rubbers that Paul used, where the penetrant uptake, the volume fraction of cyclohexanone absorbed by this rubber is about 72 volume percent. So it's only 18% polymer. The rest of it is solvent. And so in a system that's highly swollen, then you do see a bit of a bend in the concentration gradient that comes about just as a result of the expression that's shown here. In the case of Rosenbaum and cotton, where the uptake of water is only about 20 volume percent, so it's much lower, then you don't see that bend in the concentration profile. So for the desalination case, the concentration profiles are essentially linear, and for the organic liquids that that absorb to a large extent in some of these cross-linked rubbers. You can see somewhat slightly nonlinear concentration profiles. The one additional point that has to be addressed in order to apply this model to experimental data, you can take the integrated flux model and the concentration profile, or you can take the flux model with the concentration profile we've just determined. You can put that concentration profile in here, work out the derivative, and develop a model for the flux of penetrant, what we've been calling JW, volumetric flux, in terms of the diffusion coefficient, the volume fraction of penetrant at the downstream and upstream side of the membrane, and the thickness of the membrane. And you would think, or you would imagine, that the flux should be inversely proportional to the thickness of the membrane. The thicker the membrane, the lower the flux, the higher the diffusion coefficient, the higher the flux, and so forth. The trick here is that in systems that swell enormously with solvent, like Paul's case and some of the others we looked at, the sample is mainly solvent at the conditions of interest. When you start to apply higher and higher feed pressure, and you build a big concentration gradient across the material, like in Paul's case, going from about 72 volume percent down to about 40 volume percent at the permeate side, over this large concentration gradient, the thickness of the membrane under actual use conditions can be quite different from what it is when it's just freely swollen in solvent at ambient condition, because there's such a concentration gradient through the membrane. And so the next little bit is in actually applying this model, is to be able to work out what is the actual thickness of the membrane when it's under the conditions of the experiment. And this is not something that's readily subject to measurement. It turns out that if there's a relationship between the dry membrane thickness, which can be measured, before you contact the membrane with any solvent or any water, you can typically measure its thickness experimentally. Also, it's fairly straightforward to measure the thickness of a membrane that's been swollen at ambient conditions in a solvent or in water. Once it's swollen at equilibrium in ambient conditions, you can typically use a micrometer or other means to simply measure the thickness. And so if the swelling is isotropic, there's a really simple relationship between this dry thickness and the so-called freely swollen membrane. That is the thickness of the membrane once it's been swollen in solvent and ambient conditions, and that relationship is given by the result that's shown here, and this just VR0 is the volume of the rubbery material when the volume of rubber in the sample when it's swollen to equilibrium in solvent and ambient conditions, and you can write that in terms of the penetrant volume fraction as shown here. But basically what this says is that the sample swells isotropically with uptake of solvent. Now that relates two measurements that one can make in the laboratory: this dry membrane thickness with the freely swollen membrane thickness, but it doesn't tell us what the membrane thickness is under the conditions of the experiment. That we have to determine by a mathematical calculation. And so we start with the result that's shown here. I put it in terms of the variables that we started with in our analysis. And what Paul has noted is that when the membrane's actually operating under a gradient in pressure during diffusion, there's a gradient in swelling, and so the actual membrane thickness is less than this freely swollen membrane thickness by as much as 40%. There can be the membrane essentially shrivels up as you increase pressure on the upstream side, and it reduces the amount of penetrant throughout the membrane except at the feed side. then the thickness of the sample goes down. Its volume, the volume of the sample goes down. Now, in Paul's experiment, the membranes were measured in cells where permeation cells where the membrane is constrained to have a fixed area. And a simple matter of conservation of mass would say that the volume of rubber in the sample at the when it's freely swollen times the freely swollen thickness and times the area of the sample, which doesn't appear in this expression because it cancels out on both sides. So if you have the area of the sample here, the term on the left-hand side is just the amount of rubber in the sample. That's freely swollen as you mount it into the permeation cell. Now, when the experiment is running, the amount of rubber, the amount of polymer in this sample is exactly the same. And so if you integrate the volume fraction of rubber across the sample thickness, and again multiply by, imagine there's an A here, that would just give you the volume of the rubber, and that has to be exactly equal to the amount of rubber that you put into the permeation cell. Now we have a model for the concentration profile, that is how the volume fraction of rubber, or 1 minus the volume fraction of rubber will be the volume fraction of solvent. We have a model for how the volume fraction of solvent changes with distance across the penetrant, across the polymer. We can put that in here and integrate it, and it gives us an expression that relates the freely swollen membrane thickness, that is, that can be easily measured, to the membrane thickness under the actual conditions of the experiment, which can be about 40% less depending on how big the pressure difference is and how big the resulting concentration difference is from the permeate side to the feed side of the membrane. And so this result can be loaded into the flux model so that the flux can be expressed in terms of the dry membrane thickness, the diffusion coefficient, and then the volume fractions of rubber in the material. Now these volume fractions of rubber can be measured, or they can also be calculated, for example, from a model like the Flory-Huggins model. And so how does this, and here's a relationship between the key equation for flux in Paul's nomenclature and in our nomenclature, so that we followed along his derivation, but I want to make sure you have this in our nomenclature as well. There is a concept here of limiting flux that is interesting and comes up in liquid permeation, particularly in organic solvent permeation through polymers. So here's the expression for flux that we've worked very hard at deriving in terms of the diffusion coefficient of solvent through the membrane. We always use W because we're thinking back to the desalination application. LD is the dry thickness of the membrane, and then the concentrations of water in the membrane at the feed and permeate side. You'd need a thermodynamic model like the Flory-Huggins model to calculate those based on the chemical potential of water or solvent in the feed and permeate side of the membrane. Now, the activity of penetrant on the permeate side of the membrane has a relationship to the feed pressure that's shown here. Remember, we said that as the feed pressure goes up, thermodynamic activity of water in the membrane on the downstream side goes down. That means the concentration of water in the membrane or solvent in the membrane goes down as feed pressure goes up. Now there's a practical limit to this. You can see that as the feed pressure goes up to really high values, the thermodynamic activity of penetrant in the permeate side of the membrane asymptotically approaches zero. So as P feed goes to infinity, then the right-hand side of this equation goes to zero. It never goes below zero, right? The thermodynamic activity can never go below zero. The concentration of penetrant at the downstream side of the membrane can never go to below zero. And so as you raise the feed pressure, you lower the concentration of penetrant on the permeate side of the membrane. And as the feed pressure goes higher and higher, the concentration of penetrant here goes lower and lower. The lowest value it could possibly have is zero. And when you hit zero for the concentration of solvent in the membrane on the downstream side, you hit a maximum flux or a ceiling flux, what's called a limiting flux in the literature. And so then the flux, no matter how much you increase pressure beyond that, the flux can't increase anymore because you've already gotten to the maximum driving force that is across the membrane. So do we see this in practice? Well, and we can connect these concentrations. This is just pointing out the connection between concentrations of penetrant inside the membrane with, for example, the Flory-Huggins model, and it shows again as activity goes to zero, as pressure goes to infinity, then that would imply, if you work through the math, that would imply that the concentration of penetrant at the downstream side of the membrane has to approach zero. And so the maximum value of the concentration or limiting flux would be when the concentration of penetrant at the downstream side of the membrane was equal to zero, and that value can be obtained as shown here. And so is this observed experimentally? And you see this actually in the organic, in the Paul and Ebrelima work, where they're looking at organic flux through swollen cross-linked rubber. You see that the flux actually doesn't increase linearly with pressure and starts to bend over and asymptotically approach the ceiling flux. And so if the pressure, the hydrostatic pressure across this membrane were increased more and more, the flux would approach a plateau value, and that would be the ceiling flux or the limiting flux that is given in the previous slide. Here's some more examples from Paul and Ebrelima's work. The reason this is important is that nowadays there is an emerging new field in membranes called organic solvent nanofiltration, or OSN. And essentially this is a field where people are using membranes to separate mixtures of organic liquids by pressure. So if you have a mixture of organic liquids like hexane and cyclohexane, and you apply high hydrostatic pressure to the feed side of the membrane, you can have a flux of those two components through the membrane and actually do a separation using such membranes that doesn't involve a phase change as you would find in distillation. So distillation would be the normal way of separating mixtures of organic liquids, and people are now starting to look at using membranes to do that because you avoid the phase change and the energy penalty that comes with that. However, and results like the ones that are shown here are being reported in the literature. There has been some confusion in this literature, even very recently, where people have attributed these sorts of flux versus pressure profiles to what they call compaction of the membrane. They're imagining that the membrane is somehow compacted, and often the membranes that are used in this case have a porous support, and they're imagining that there would be resistance from the porous support, when in fact what they're seeing is a phenomena that has been widely reported in the literature, but almost 50 years ago. And I think there's a lesson in that there's some misreporting of results in the organic solvent nanofiltration literature, I think by people who aren't aware of this work. Fortunately, you will not have to go through life with that ignorance, thanks to the time we've spent together working through this. I appreciate your patience with it. Here's another example showing, in the case of methyl isobutyl ketone, a real nice approach to the ceiling flux. And the reason that you can see that in these organic in the cases of these organic systems is the fact that the partial molar volume of the solvent inside the polymers, for the organics, the partial molar volumes are, can be on the order of 100 cc's per mole, 200 cc's per mole, and the bigger the partial molar volume is, then the greater is the effective pressure on this thermodynamic activity. Now, we started out by looking at the by posing this problem in the context of desalination, and so the question is, could you observe this in a situation where water were the penetrant of interest? Now, water has a partial molar volume to first approximation just equal to the molar volume of water, 18 cc's per mole. That's 1 gram per cc and 18 grams per mole. And if we keep the permeate pressure at 1 atmosphere, what you would find is that in order to see the limiting flux, you would have to, the pressures that would be required to drive the water activity anywhere near zero, and that would be the point where you'd start to observe the limiting flux, are just at pressures that are so far above where desalination is normally done that you would never observe limiting flux in water purification membranes, and that's because the partial molar volume is only about 18 cc's per mole. You do see it in the organics when you have much larger partial molar volumes, and since desalination is done in about less than about 100 bar, look at the shape of this curve. The water activity is essentially decreasing linearly here in the beginning part of this curve. If you did a Taylor series expansion on this term, the first term would be linear, and that's essentially the region we operate in for desalination, and is essentially why the water flux across the membrane is a linear function of pressure. You're in this linear region of how water activity, and you're at low concentrations of water, relatively speaking, so water activity is proportional to water concentration. So as you raise the feed pressure, you linearly lower the water concentration on the downstream side of the membrane. You linearly increase the gradient driving transport, and then the water flux is just directly proportional to the gradient, and so therefore the water flux is linearly proportional to pressure, which is what's observed experimentally. This is just to clean this up a little bit and finish it. This is showing Paul's model, our model for liquid permeation through swollen membranes, is showing the comparison of that model with the experimental data. And so what's being plotted is the measured flux, and Paul measured volumetric flux as a function of the volume fraction difference or concentration difference between the solvent in the feed side and permeate side of the membrane, and this was calculated based upon the pressure of the solvent and the Flory-Huggins model. We'll come back to that again just a bit later. This is again more comparison of those data with the model. And this model was proposed based on a constant diffusion coefficient, and so to the extent that these curves are linear, that suggests that that's a reasonable approximation to modeling transport in a complex place. Here's one more set of results showing good agreement with the model and the experimental data. Now, for the next part of this, we're going to be asking the question, what does salt do to this picture? Because again, we posed this problem originally in terms of desalination. So we have a membrane that's exposed to a saltwater mixture. We apply pressure to the feed side of that mixture, permeate mainly water, but a little bit of salt. What does having a solute like salt in the solvent do to the thermodynamic picture that we've developed here? And it turns out that that it has actually uh, very little impact on the general nature of what we have, what we've discussed. And the only thing the salt does it acts to modulate the thermodynamic activity of the penetrant that is in the feed and permeate solution surrounding the membrane. Essentially, for all intents and purposes, for desalination, the presence of the salt does little to change the actual transport of water inside the membrane. And so that's why we've kind of walked through this process on water transport by itself, just looking at pure water, without considering the salt, is because the salt adds a, uh, a minor complication to that picture, but doesn't change the big features of it. And so it's a little bit easier to see the basis for liquid-driven transport if you don't have any other solutes in the picture initially. And so we will next look at this through the lens of osmosis, which is the way the impact of salt on the activity of a solvent, or the impact of salt on the thermodynamic activity of water, is often described. Um, examples of osmosis are, if you took like strawberries and slice them up and then put sugar over them, you come back sometime later and the berries have shriveled, and there's a solution of sugar water outside the berries, and that's the sugar acting as an osmotic agent to essentially dehydrate the fruit. And also the transport of fluids across cell membranes is governed by osmosis. The way water gets up through trees into the leaves, governed by osmosis. Um, and just take you back a little bit to high school chemistry, perhaps. We consider a membrane that has two aqueous solutions on either side, and the membrane is permeable to water but not to salt. And we put salt water on one side of the membrane and fresh water on the other. And if we just keep this system at, for example, ambient pressure on both sides, the tendency is for the fresh water to cross the membrane to try and dilute the salt out of the water on the salt water side, because the concentration of water on the salt water side is lower than it is on the freshwater side. That means that the chemical potential of water on the freshwater side is higher than it is on the saltwater side, and so that's going to drive the transport of water through that membrane. If we apply a hydrostatic pressure to the salt water, we can actually, that hydrostatic pressure, as we have seen, can drive the flow of water across the membrane. And if we apply a hydrostatic pressure that is just sufficient to keep any of the fresh water from coming across the membrane, that hydrostatic pressure would be called the osmotic pressure. And for an ideal solution of ions in water, we calculate the osmotic pressure as RT times the concentration of ions in water. This has an analogy to the ideal gas law, and it comes about from ideal solution theory, as you might recall. And so this osmotic pressure is directly related to the concentration of ions in the water. Ions often behave non-ideally, and so this expression is often modified with an activity coefficient on the right-hand side, or a so-called osmotic coefficient that takes into account non-ideal behavior of activity, the activity of the ions. If we apply a hydrostatic pressure that is greater than the osmotic pressure, then we can actually drive water from the saltwater side of this membrane to the freshwater side of the membrane. We can drive water uphill from a concentration point of view because we've applied a hydrostatic pressure that's greater than the osmotic pressure, which would normally be trying to drive the water from the freshwater to the saltwater side. And we would see that the flux of water was then linearly proportional to the difference in hydrostatic pressure minus the difference in osmotic pressure between these two aqueous solutions. We distinguish several regions of transport. If we were to plot the result on the previous slide in terms of water flux versus the transmembrane pressure drop for a given salt concentration in the feed and permeate side of that membrane, or on the saltwater and freshwater side, if we have no hydrostatic pressure drop imposed, then we would have a water flux that on this scale, for those of us interested in reverse osmosis, this water flux would be negative, indicating that the water is moving from the freshwater to the saltwater side of the membrane. As we start to increase, for example, the feed pressure, holding the permeate pressure equal to atmospheric, or increase the pressure on the saltwater side of this membrane while holding the pressure on the freshwater side constant, then we would start to reduce that water flux from the freshwater to the saltwater side. This is a regime that in the literature is referred to as pressure retarded osmosis. That is, you don't get quite the osmotic flux because you're applying hydrostatic pressure that's acting against it. And when that hydrostatic pressure difference is exactly equal to the osmotic pressure difference, then the water flux across the membrane is zero. And if you apply an even higher pressure difference across the membrane, then you enter the regime of reverse osmosis, which, as the name implies, is opposite of osmosis, where now the water is being transported against its concentration gradient from the saltwater to the freshwater side. And the more hydrostatic pressure difference you apply, the greater is the water flux. This also is quite reminiscent of an experiment I spoke with you about in the first day or two of our time together, and that is the Abbé Nollet's experiment. So this is not restricted to just salt and water. In this case, the Abbé Nollet had an alcohol-water mixture separated by a pigskin bladder from pure water. And because the water concentration inside this vessel is lower than it is outside, and the membrane is more permeable to water than alcohol, there is a driving force that can be expressed in terms of an osmotic driving force for water to permeate into this chamber. And the Abbé Nollet saw his pigskin membrane stretched to the point of bursting. One often measures an osmotic pressure of a solution by exposing it across a membrane that's permeable to the solvent but not the solute in a pure solvent bath, and then measuring the hydrostatic pressure that is required in order to get zero rate of solvent transport across the membrane. And this the hydrostatic pressure induced by this level of solution above that of the solvent bath just gives the osmotic pressure directly. To give you some ideas of what values of osmotic pressure are typically observed in nature. So if you had a sodium chloride solution that is isotonic, and that means that it would have the same osmotic pressure as your blood, you would need about this much sodium chloride in pure water to make a solution that has the same osmotic pressure as your blood, and that would have an osmotic pressure of about 8 bars. So think about that the next time you're walking around. Your little osmotic pumps with in your bloodstream, the osmotic pressure is about 8 bar. Brackish water has osmotic pressure around 1 to 2.7 bar. Seawater is on the order of 23 bar. And so if you're doing seawater desalination by reverse osmosis, what this means from a practical point of view is you have to apply hydrostatic pressure differences across the membrane greater than the osmotic pressure before you see any water flow at all and across the membrane. And so these seawater desalination membranes operate typically at pressures that are significantly above the osmotic pressure. And just as an example of a non-ionized solute like sucrose, to give you an example of what its osmotic pressure would be, these are all based on the ideal solution expression for osmotic pressure. We're going to talk briefly through a thermodynamic analysis of osmotic pressure, but I believe I've already overrun my time by a minute or two, so I'm going to save this for next time and look forward to continuing this discussion with you. Thank you.